In 2024, a team of researchers led by geophysicist Vachon, right at the University of California, San Diego, working alongside Michael Manga at UC Berkeley, went back through the InSight seismic data with a specific question in mind. For years, planetary scientists had puzzled over an uncomfortable piece of missing arithmetic. Orbital imagery and geological evidence make it overwhelmingly clear that ancient Mars once had enormous quantities of surface water. Rivers that carved valley networks still visible from orbit today, lakes that filled craters like Jezero, and quite possibly oceans covering large portions of the northern lowlands. But when scientists tried to account for where that water actually went, the math never quite balanced. The Martian polar ice caps, while substantial, do not contain nearly enough frozen water to explain the scale of ancient surface water evidence. Some of that original water was undoubtedly stripped away into space by the solar wind after Mars lost its protective magnetic field. But atmospheric escape rates, even calculated across billions of years, could not account for all of it either. A significant fraction of ancient Mars's water was, quite simply, unaccounted for, missing. And planetary scientists had long suspected it might not have vanished at all, might have gone down. Using a physics model borrowed directly from techniques the oil and gas industry has spent decades refining to search for underground reservoirs on Earth. Right, Manga, and there. Colleagues analyzed how seismic waves from Marsquakes behaved as they passed through the middle layer of the Martian crust. Roughly 11.5 to 20 kilometers beneath the surface, their model tested various possibilities for what could be filling the pore spaces within that fractured, cracked layer of rock, dry rock, ice, or liquid water, and compared each scenario against the actual seismic behavior InSight had recorded. The result was unambiguous. Dry, empty rock did not match the data. Ice did not match the data either. The seismic signature that best explained what InSight had actually measured was rock saturated with liquid water. Water occupying the countless microscopic cracks and pores within that layer of fractured Martian crust. Exactly the kind of underground reservoir geologists search for when drilling into similar rock formations here on Earth. The scale of what the model suggested was almost difficult to comprehend. If the estimated water content of that crustal layer were somehow extracted and spread evenly across the entire surface of Mars, it would form a global ocean between 1 and 2 kilometers deep. To put that in perspective, that is potentially more liquid water than every ocean, lake, and river currently on the surface of Mars. Combined, except this water isn't on the surface at all, has been sitting there, hidden beneath the red dust, for what may be billions of years, quietly filling the cracked bones of an ancient, broken world. The researchers were careful, appropriately and necessarily careful, about the limits of what this discovery actually confirms. The data comes from a single landing site, Elysium Planitia, and while the underlying physics is well established, extrapolating results from one location to the entire planet carries genuine uncertainty. It remains one of the most significant open questions raised by the discovery itself. Is this deep water reservoir a global feature of Mars, or a phenomenon localized to the region where InSight happened to land? Additional missions, ideally seismometers placed at multiple locations across the planet, would be required to know for certain. Science does not settle for a single data point when the question is this important, and researchers have been explicit that confirming a truly global reservoir will require exactly that kind of expanded seismic network. A mission that does not yet exist, but that many scientists now consider one of the most urgent priorities in Mars exploration. Still, even with that uncertainty acknowledged, the implications of what InSight uncovered are difficult to overstate. Because buried within this discovery is a question even larger than where ancient water went. It is a question about whether that water might still be capable of supporting something alive. On Earth, scientists have spent the last several decades systematically overturning almost every assumption we once held about where life can and cannot survive. Deep beneath the ocean floor, in rock formations kilometers below sunlight, in water so hot it would boil at the surface, in environments utterly starved of oxygen, we have found thriving microbial ecosystems, organisms that draw energy not from the sun, but from chemical reactions occurring in the rock itself. This entire category of subsurface life, collectively known as the deep biosphere, is now understood to represent an almost unimaginably vast portion of Earth's total biomass, an entire hidden ecosystem operating far below our feet. That most of human history unfolded without anyone even suspecting it existed. If liquid water can persist within the cracked Martian crust, sheltered from the deadly radiation that scours the surface, potential lie warmed by residual heat from the planet's interior, then the fundamental question shifts. It is no longer only about whether ancient Mars, billions of years ago, briefly had the conditions necessary for life to emerge at the surface. It becomes a question about whether a deep subsurface Martian biosphere, similar in principle to the one we have discovered hiding within our own planet's crust, could have survived undetected, isolated, and enduring for billions of years after the surface of Mars became the frozen, radiation-blasted desert we see today. Nobody has found evidence of that. This is critical to say clearly and without exaggeration. The InSight discovery confirms the presence of liquid water within the Martian crust. It does not confirm, suggest with strong evidence, or provide any direct indication of biology. The leap from liquid water to living organisms is enormous, and scientists are careful to describe this finding purely in terms of what it demonstrably shows: a previously unknown reservoir and a compelling resolution to Mars's decades-old missing water mystery. But water is, without exception, the single non-negotiable requirement every scientist agrees any form of life as we understand it would need. And for the first time, we have direct physical evidence, not inference from orbital photographs of ancient dry riverbeds. But on Mars today, right now, in this exact era of the planet's history, not billions of years in an unreachable past, this changes the entire calculation for where future missions should look. And it collides directly with an uncomfortable practical the reality that mission planners have wrestled with for decades. How do you responsibly search for life in a place you cannot safely reach? The water InSight detected sits 11.5 to 20 kilometers beneath the surface, depth so far beyond current drilling technology that it makes even NASA's most ambitious sample return architecture look almost quaint by comparison. Nothing humanity has ever built, not on Earth, not anywhere, drilled a hole that deep on a remote robotic mission millions of kilometers from home. The deepest borehole ever drilled on Earth, the Soviet Union's Kola super-deep borehole, took nearly 2 decades to reach roughly 12 kilometers, using the full industrial infrastructure and continuous human oversight available on our own planet. Replicating anything close to that feat autonomously on Mars is not a near-future mission, may not be a near-century mission. And this raises a genuinely difficult tension at the heart of Mars exploration, one that planetary protection officers within NASA take extremely seriously. If liquid water exists within the Martian crust, and if there remains any possibility, however small, that microbial life could exist within it, then any future mission attempting to reach that water carries real risk of forward contamination. The possibility of introducing Earth microbes into a pristine Martian environment, permanently compromising our ability to determine whether anything found there is truly native to Mars or something we carried there ourselves. International planetary protection protocols, first established during the earliest era of space exploration and continuously refined since, exist specifically to prevent this outcome, and the InSight discovery has only intensified debate within the scientific community about how those protocols will need to evolve as our technical capability to actually reach deep subsurface water eventually catches up with our theoretical understanding of where to find it. It is worth pausing on the sheer strangeness of the method that revealed all of this. No rover drove across that crustal water. No drill touched it. No camera ever photographed it, because it cannot be photographed. It sits far too deep beneath opaque rock for any imaging instrument to reach. Humanity discovered an ocean's worth of hidden water on another planet purely by listening, by placing a single extraordinarily sensitive instrument on the ground and patiently recording the way that planet trembled every time its crust cracked, every time a meteorite struck its far side, every time deep ancient stresses inside its interior finally released. It is, in its own way, one of the most profound examples in the history of science of indirect discovery, proof that some of the universe's best-kept secrets are not hidden from our eyes. They're hidden from our ears, waiting for an instrument sensitive enough and a team patient enough to finally listen. This also reframes something fundamental about how we should think about Mars itself. For half a century, the story we told about the red planet was a story of loss, a world that once had rivers and lakes and possibly oceans, that once had a magnetic field and a thick atmosphere, and then lost nearly everything that made it hospitable, leaving behind a frozen, wind-scoured shell of its former self. That story is not wrong, but it may be radically incomplete. It may be that Mars did not lose its water so much as it hid it, sealing an entire ocean's worth of liquid within its own broken bones, tucked away from the destructive solar wind and radiation that scoured everything at the surface. Preserved in darkness for billions of years while the world above it withered into desert. If that is true, then Mars is not simply a graveyard of what it used to be. It may be something stranger and more compelling, a planet with a hidden second act, an interior that never stopped holding on to the one ingredient every search for life ultimately depends on, quietly waiting for an instrument sensitive enough to notice it was there all along. The scientists behind this discovery have been careful to frame it not as an ending, but as the opening of an entirely new chapter in Mars exploration, one that will require missions fundamentally different from anything flown before. A single seismometer at a single location gave us this. Multiple seismometers positioned across different regions of the planet could reveal whether this reservoir is a localized anomaly or evidence of a truly global planet-spanning water system. Advances in deep drilling technology, and eventually perhaps, which means that right now, today, this discovery exists in a genuinely rare state for modern science. We know something remarkable is true, and we do not yet possess the technology to go find out what it means. An ocean's worth of liquid water is sitting inside another planet, confirmed not by imagination or speculation, but by rigorous seismic analysis and peer-reviewed physics. And it will likely remain entirely out of reach for the rest of most of our lifetimes. There is something almost poetic in that. Humanity spent decades staring up at Mars. At that faint red point of light our ancestors once mistook for a bleeding war god, imagining canals, imagining civilizations, imagining a world just active enough, just alive enough, to hold something like us. Then we sent our machines, and one by one, those fantasies were stripped away by cold, honest data, until Mars became, in the public imagination, simply a dead world, a cautionary tale, a monument to what a planet loses when it can no longer protect itself. And then, quietly, patiently, using nothing more dramatic than a microphone pressed against the ground, we discovered that the fantasy wasn't entirely wrong. Mars is not dead. Not fully. Somewhere beneath its silent red surface, in the dark, in the cracks of ancient broken rock, something is still there. Water at minimum. And water on every world we have ever studied closely enough to check has a habit of eventually leading somewhere far more interesting than anyone expected. We do not know if anything lives in that hidden Martian ocean. We may not know for generations. But for the first time, we know it is there, waiting in the dark. Exactly where the oldest question in planetary science always suspected it might be hiding all along. Beneath the red dust of Mars, roughly 11 to 20 kilometers down, scientists have found something that should not exist on a planet we have spent 50 years calling dead. Liquid water, not ice, not a memory of water frozen into ancient minerals. Actual liquid water, seeping through cracked and fractured rock. In a quantity so large that if you could somehow pump it all to the surface, it would drown the entire planet under an ocean more than a kilometer deep. This is not science fiction. This is not speculation dressed up as fact. This is a peer-reviewed conclusion, drawn from 4 years of data collected by a spacecraft that never moved, using a method borrowed from the science of earthquakes. On a planet where nobody expected to find quakes at all, to understand how humanity found an ocean's worth of water hiding inside another planet without digging a single hole. You have to go back to a lander that touched down on a flat, featureless plain called Elysium Planitia in November 2018, carrying an instrument so sensitive it could detect ground vibrations smaller than the width of a hydrogen atom. The mission was called InSight, and unlike the rovers that came before and after it, InSight was never designed to explore. It was designed to sit perfectly, motionlessly still, and listen. Every planet has a heartbeat, a slow, continuous trembling caused by shifting rock deep within its interior, and on Earth, we call that trembling an earthquake. For decades, scientists suspected Mars might have its own version, Marsquakes, but nobody had ever managed to detect one. Because unlike Earth, Mars has no network of seismometers scattered across its surface, no century of accumulated data, no way to confirm that the planet was, geologically speaking, still alive. InSight carried a single, extraordinarily sensitive seismometer called SEIS, built by the French space agency CNES, and its job was almost absurdly simple to describe and staggeringly difficult to execute. Place this instrument on the Martian surface, shield it from wind and temperature swings that could drown out the signal, and wait for the ground to move. The team behind the mission, led by principal investigator Bruce Bannert at NASA's Jet Propulsion Laboratory, spent decades pushing for a seismology mission to Mars. Watching proposal after proposal get passed over in favor of more visually spectacular missions, rovers with cameras that could capture the kind of dramatic imagery that wins headlines and secures budgets. A stationary lander listening for whispers in the ground was, by comparison, a difficult mission to sell. It offered no rover tracks crossing alien dunes, no daring sky crane landing, no helicopter buzzing across a crater floor. It offered patience. But patience, it would turn out, was exactly what this particular mystery required. InSight's first attempt to deploy its heat probe, an instrument nicknamed the Mole, designed to hammer itself 5 meters into the Martian soil to measure heat flowing from the planet's interior, ran into serious trouble. Almost immediately, the Martian regolith at the landing site turned out to be far more compact and different in composition than mission engineers had modeled, and the Mole struggled to gain traction, bouncing in place instead of burrowing downward. Engineers spent nearly 2 years troubleshooting the problem from 200 million kilometers away, attempting increasingly creative fixes, including using the lander's robotic arm to physically press down on the Mole to help it dig. Before ultimately, in January 2021, the team made the difficult decision to abandon the heat probe experiment entirely. It was a genuine failure, a reminder that even missions built around patient listening are not immune to the harsh unpredictability of operating machinery on another world. But the seismometer succeeded where the Mole could not, and it began delivering results almost immediately after InSight touched down. On April 6, 2019, just months into the mission, SEIS detected a faint, unmistakable tremor rippling through the Martian ground, the first confirmed Marsquake in human history. It was a landmark moment, quiet and unglamorous compared to the roar of a rocket launch, but every bit as historic because it proved, for the first time, with hard seismic evidence, that Mars was not a geologically frozen corpse. Something inside that planet was still moving. Over the following 4 years, before InSight's solar panels finally became too coated in Martian dust to generate sufficient power, and the mission was declared complete in December 2022, SEIS detected more than 1,300 Marsquakes. Most were small, subtle tremors, but some were significant, including one in 2022 that registered as the largest quake ever recorded on another planet, and remarkably, another quake detected that same year that scientists eventually determined was caused not by internal geological forces at all, but by a meteoroid impact on the opposite side of the planet, strike violent enough to send seismic waves rippling clear through the Martian interior and register on InSight's instrument, thousands of kilometers away. It was, in effect, humanity's first glimpse of a live impact event shaking an entire alien world, captured not by a camera, but by sound. Each of those 1,300-plus tremors carried within it something extraordinarily valuable, information about the material the seismic waves had passed through on their way to InSight's sensor. This is the same fundamental principle that seismologists have used for over a century to map the interior of our own planet. Seismic waves travel at different speeds and behave differently depending on whether they're passing through solid rock, molten rock, or rock saturated with liquid. By painstakingly analyzing the timing, speed, and behavior of Marsquake signals as they traveled through the Martian interior, scientists could essentially build an X-ray image of the inside of an entire planet without ever drilling a single borehole. This seismic dataset had already produced one landmark discovery years earlier, when researchers used it to measure the size and physical state of the Martian core for the first time. confirming it to be far larger than some earlier models predicted and, most strikingly, still at least partially molten. A finding published in 2021 that reshapes scientific understanding of how Mars formed and why. Its magnetic field died out so long ago, but buried within that same trove of seismic data was a second mystery, one that took longer to unravel, one that involved not the deep hidden core thousands of kilometers below the surface, but a layer far closer to home, the Martian crust.